Hello everyone and welcome. Today I am presenting our work on the design, manufacturing and multiphase dynamics of the Unmanned Aerial Aquatic Vehicle or UAAV. This project is funded by ANRF under the SUPRA scheme. I am Dr. Joydeep Bhowmik, Principal Investigator representing the Department of Aerospace Engineering and Applied Mechanics at IIEST Shibpur. Alongside my co-PIs, Dr. Debnath and Dr. Prince Lawrence Raj. Our research tackles the dual medium challenge, bringing the massive gap between atmospheric flight and aquatic motion. Nature solved this millions of years ago. Birds like the gannet plunge into the ocean at high speeds, while traditional robotics forces us to choose to either fly or swim. Our objective was to mimic this biological versatility to create rapid deployment, fully submersible vehicle capable of both extended aerial reconnaissance and deep underwater navigation. This indigenous development relies on the deep synergy of our research team at IIEST Shibpur. Together with my co-PIs and the dedicated work of our PhD research scholars Nishant Gupta and JRFs Pankaj Kumar and Shubhadeep Sarkar, we have combined expertise in aerodynamics, structural design and multiphase fluid dynamics to execute this end-to-end systems engineering project. To fundamentally operate in two different fluids, we engineered a rigid fold-level architecture. UAAV utilizes a spring-loaded wings and a V-tail, making it capable to be launched from a catapult or a compact tube. The most critical feature in its drag reduction mechanism, the wings completely retract upon the water entry to minimize the hydrodynamic resistance, facilitating deep submersion. We have officially filed a patent for this tube launchable folding wing design with its dedicated dual propulsion system. Designing this vehicle introduced a major paradox. Increasing the battering capacity boosts endurance, but added weight exponentially increases the power consumption required to stay in the air. Our goal was to find the exact sweet spot for the payload. As you can see in our parametric charts, reducing the empty airframe weight by just 10% yields a disproportionate, massive increase in the overall range. More importantly, the lift to drag ratio acts as an efficiency multiplier. By optimizing our aerodynamic sharpness to a lift to drag ratio of 12, we maximize our flight time without exceeding the structural limits of the aircraft. A fundamental law of fluid mechanics states that we cannot use the same propeller for both air and water because of the extreme density differences. We solved this with a dual propulsion system. For flight, we indigenously fabricated a custom foldable propeller with molded carbon fiber, epoxy and 3D printed components. It uses centrifugal force to snap open during the launch and folds perfectly flush against the fuselage upon water entry to eliminate drag. Wind tunnel testing validated its operational efficiency at an impressive 50 to 60%. Underwater, a dedicated secondary marine propeller takes over, which we optimized using a custom floating test bench in a lake. The most violent phase of the mission is the plunge. High aspect ratio wings create catastrophic drag and structural stress upon hitting the water, which is why our wings dramatically fold just before the entry to manage the immense impact acceleration. Using Eulerian volume of fluid simulations, we map the transient turbulent kinetic energy during this transition. These CFD contours reveal a critical ground effect instability. Operating the propeller just inches above the water at a height to radius ratio of 0.3 introduces massive free surface deformation, causing high amplitude oscillations in lift and drag that the flight controller must actively counteract. To validate these complex computational models in the physical world, we faced a major hurdle. Commercial data acquisition systems were either too slow to capture the high speed impact, or too bulky, or too expensive. Our solution was to build the hardware ourselves. We developed a completely indigenous 15 channel 16-bit hybrid ADC, analog to digital converter based pressure scanner, capable of up to 10 kilo samples per second for each sensor, plus minus 5% of full scale accuracy. This tooling allowed us to perfectly measure the impact pressure on the hemispherical nose in our water tank setups, matching our digital models to our physical reality. This slide perfectly illustrates the complete dive sequence. The UAAV executes a 30-degree pitch down approach, fully compacts its wings and pierces in the water, and then transits into a submarine mode. On the left of our data, the precise evolution of the pressure on the nose at the impact velocity of 5 meters per second across different entry depths provides structural viability of our design. Of course, the theory must meet practice. Here is our first physical prototype undergoing successful RC flight testing, proving the stability, aerodynamics efficiency, and practical deployment of the rigid foldable wings architecture in the real world. The downstream societal and technological impact of this platform is also immense. From the contained tube storage to the media deployment, it can fly long distances, drive into aquatic oceans to gather data, surface back and fly again. This completely eliminates the need for heavy expensive marine equipment. It offers rapid deployment, operational advantage that is highly attractive to border reconnaissance and defense, as well as serving as a vital, sustainable tool for tracking pollution and monitoring water quality in inaccessible lakes and oceans. We extend our deepest gratitude to ANRF and SERB Supra scheme for their critical support financially, and to the IIEST Shibpur for their institutional backing. Thank you to the evaluation committee and viewers for your time. We invite you to review our patent and recent publications in the leading journals like Ocean Engineering and the Journal of Engineering for the Maritime Environment to explore deep science behind this UAAV. Thank you.